lecture 7. So, hi everyone, I'm Su-Tim Lee, and I will be leading this lecture 7, Introduction to Wind Wave Modeling. Okay, so first, here are the links to both our user's guide and the theory document of EFDC Plus. So people can always use both of the documents as references as we go along. Okay, so at the very beginning, I will go through the conceptual framework of the wind waves, go through the physical phenomena that EFDC can model, and also some of the very basics waves theory, just a very introductory level to let everybody know some of the major physical phenomena of water waves. And then followed by that, I will start introducing the EFDC plus wind wave module, explaining how EFDC make all those computations in the background. And then following by the introducing the wave module interfaces and go through all those parameter settings and all those button and knobs. So as wind blows through a water surface, because of friction between the air and water, it can start to drag water along, and by wind itself, it can cause currents and then recirculations over reservoirs, lakes. But when you have a large enough wind that's blowing constantly over a vast area for quite amount of time, those little waves can gradually being picked up and develop into larger waves or swell even. So just like as you go to coastal or estuaries, except for those very chaotic wave breaking or sloshing movement at the very near shore, you look a little bit further, sometimes you can see those very beautiful and periodic swell that's coming in. And so those are mostly developed way far from the shore, and those are generated by distant storms and instead of the local wind. And so you can see that those circular motions, those are representing the particle motions under the wave, and you can see that gradually develop into a more elliptical shapes, and then even more close up shore until the wave starts to break. And those are the transformation from deep water waves to shallow water waves, which we will go through more detail later on. So because of the wave motion, because of the wave, it affects the particle movement. So it can also affect bad shear stress, and it can also cause currents. And of course, the mixing process might change and the sediment resuspensions. So it becomes a more important factor when you're modeling over areas such as estuaries and coastal areas, and even for a large lake, I would say. So here's the very basic wave properties. Here we have a sine wave, and we all know that this represented the wavelength, and the time that a wave passed through this is the period. And then the wave height is from the crest to trough. However, the real world, the wave can, you won't see this kind of sine wave in the real world. is generally being added up with multiple of different sine waves with different frequencies and different energy, different wave height. And so it becomes more sense to describe the wave height and the frequency in a more statistical way. And so here is two, like on the left side is a series of data that I download from the NDBC, National Data GUI Center. And the graph on the right side is the wave spectrum. So instead of measuring the height from trough to crest, the wave height used here, here is actually the significant wave height, and it's defined it as average of the highest 1/3 of the wave. So for NDBC, they collect the wave data every 20 minutes, and through that 20 minutes, you can have different heights of the wave passing through the sensor. So by collecting all those wave heights and you calculate the average of the top highest 1/3 of the wave, that's the significant wave height that's being recorded at here. And it's also the 4 times of the root of the area of wave spectrum times 4. So here you see this is the wave spectrum. So the y-axis represents the wave energy density, and the x-axis is the wave frequency. So because waves come from during this 20 minutes period, waves can come from different directions and have different kind of frequency, and they add it up as the CSAT that we see. So when you look at the second column here, the dominant wave period, it is actually means that it's the period that corresponding to the frequency band with the maximum value of spectral density, which should be this frequency that you can see here. So that's how those most important wave properties being recorded for this data set. There's also other different kind of wave height. People might use the root mean square of the wave height, and people might use instead of the highest 1/3, people can use highest 1/10. So it depends on how people are going to utilize the data and what kind of design they are going to make. But yeah, this is kind of giving people a general idea of how wave properties are being measured and collected through, at the actual buoys. So another important factor is the wind fetch. So as I said, when wind blow over a water surface, it usually starts with the capillary wave, and then as it's blow through constantly over a period of time and over a large enough area, it can gradually develop into larger waves. And those larger waves, based on the dispersion relationship, it can start to separate into swells. So that's why people often see those constant period of wave that's traveling towards the shore. Those are the well-developed wave group that is founded at a very distant shore. So the wind fetch, the definition is an unobstructed distance wind can travel over in a certain directions. And in EFDC+, the internal wave module, the fetch length is calculated from the land boundary to the cell in the upwind direction. So later in the hands-on session, the material provided is by using the external wave model, which is using the swan, but you can also try to test it using the internal wave module, and then you will have a better sense of how this fetch length it's being calculated. And then followed by that, this graph shows the movements under shallow water waves and deep water waves. So as I mentioned earlier, as wave travel towards the shore, the wave particle, the particle movement under the wave gradually changes from the circle to a more elliptical motions. And one of the main things that separates from deep water wave from shallow water waves is not just by the depth of the water, it's actually by the kind of like a relative depth. So here you can see that K is the wave number, it's 2 pi divided by the wavelength. And then it's actually when the depth of the water divided by the wavelength, when it's over 0.5, it's considered as a deep water waves. And then as you travel, as the water becomes more and more shallower, it transforms into a shallow water waves. So one of the main points is that it's not the actual water depth that's being defined as a shallow water waves or the deep water wave. It's kind of this relative water depth that's defining the shallow and deep water waves. And these are all derived from a linear wave theory. So there's lots of limitations and assumptions in linear wave theory, such as it assumes that water is inviscid and incompressible and irrotational, so that you only see that those kind of closed loop motion. But we know that things travel on the wave can gradually be swashed on shore. And so that's more related with the Stokes drift, which is not a linear process, but a more second order or higher order nonlinear processes. And the last important phenomenon is the radiation stress. So it is called radiation stress, but it is actually the wave-induced momentum flux that's generated by the wave itself. So it's only called stress because of the unit. It's divided by the unit length of x or y directions. So it was first published by Longier-Higgins in 1964. And what important is about radiation stress is that as the wave travels through a mild slope bathymetry, the wave setup and set down can be significant. So the wave setup is that the mean water surface, the mean sea level can decrease when the wave reaches its breaking point. And then after it breaks, because the energy starts dissipating and the mean sea level will start generally rise up towards the shore. And so that's the whole wave setup and set down phenomenon that can occur. And it becomes pretty important when there's a storm surge, and while the bathymetry of the beach is relatively flat with a very mild slope, and those can, at that kind of situation, this can become a really important factor that needs to be taken into considerations. And another thing is those wave-induced current, which include those longshore current and the rip current. So the longshore currents, when a wave came into the shore with an angle, and it generally pushes all the sediments towards one direction of the shore, and that's what we call longshore current. And another rip current is that at some locations along the shore, they will have a strong current that drags people away from the shore, and that's also one phenomenon that's related with the radiation stress. So after introducing those those basic physical phenomenons, now I'm going to show you the wave module structure under EFDC+. So in EFDC+ wave module, users can choose to use internal wind wave model or the external wave model. And for both model, users can also choose to calculate it with or without the radiation stress. So I will start to explain what's the differences between internal wind wave model and the external wave model. So for the internal wave model, EFDC Plus is actually using a empirical model, and it is solely based on the wind speed and the fetch length. And there's two assumptions that's being made for this particular model. So it assumes that the duration is long enough that the wind blow in the one direction. It's long enough to let the wave to reach an equilibrium condition. So this assumption means that in the internal wave model, the wind direction is actually the same as the wave directions. And another thing is that because of this kind of assumption, the wave refraction, diffraction will not be taken into consideration under the EFDC Plus internal wind wave model. And another thing is that the wind speed and water depth are assumed to be spatially uniform over the fetch. And since EFDC Plus is calculating the length between the cell to the land boundary, so this basically means that, within the same cell, that the wind speed and water depth, it's uniform. So this is how the internal wind wave model works. It is not a physical based model. It is just an empirical model. So you won't be able to see every wave motion in much detailed form. So EFDC Plus provide the users another options of external wave model, and for this EFDC Plus is using the SWAN, which is called simulating waves near shore. So this is a third generation phase averaged wave model, and it's been generally used for over different kinds of near shore or shallow water applications, and it's pretty well known, and it's constantly being under maintained, and they have an open source on their own website. So if you can compile it, then you can always get the most updated SWAN model. So it solves the wave in a spectral model, so spectral and energy spectral model. So on the left-hand side, you can see that it it calculates the total derivative of the wave action, and on the right hand side you can see all kinds of energy that related with the wave. So you can see that the wind growth and the dissipation because due to the white capping and other nonlinear interactions and bottom frictions and the dissipation of energy when the wave breaks. So it is it is a well-rounded physical model that takes into most of the physical properties of the wave. But one of the caveats of using the external wave model is that currently EFDC still doesn't allow users to perform a online coupling with the SWAN. This means that users need to finish their SWAN model run first and then input those results back into the EFDC for EFDC to calculate other sediment movements, Stokes drift based on the SWAN model result. Yeah, so that's one of the main caveats that EFDC now has, and we're still trying to develop a more dynamic coupling between EFDC Plus and SWAN so that they can communicate it between each step, but that will be coming in the future. But the internal wind wave model that I just mentioned is indeed coupled with the EFDC Plus hydrodynamic and sediment transport part. So basically, the EFDC Plus wave module, the features included that one internal wind wave model and the external wave model, and users can select that if they want to calculate radiation stress or not. And then one of another feature is that because wave computation, especially when you're using SWAN for wave calculation, it can become very computational expensive. So EFDC Plus also allows users to define a particular subset to compute the wave effects. So you don't really need to compute the wave effects throughout the whole model if let's say, as example, you are just modeling a estuary, then you can select only the coastal part to model the wave effects instead of modeling the whole to reduce the computational time. And to let users to have a better user experience to couple with the external SWAN model, EFDC Plus in the GUI, it allows users to generate all those SWAN input files, all those required input files for SWAN to run. And then, of course, you need to load it back in. So EE has the capability of importing all the wave model results from SWAN too. So then now I'm going to go through some of the basics knobs and parameters in the GUI interface. So this is the first window people will see. Here, it allows users to select internal or external wave module. And by here, the checkbox, users can define that if they want to include radiation stress to calculation or not. And then it pops up other additional parameters for users to set up. So here, these are actually just like a on and off option. So those are not like parameter values that users going to input. So like this is 1 means that it's going to calculate the rotational radial stress, and then 0 is that it's not going to calculate it, that stress. And so is this moving bed effect. But like these two, those are actually values that represent of that parameter. So here can be a little bit confusing, and we're still we'll still working on to improve the overall user experience at here. But as you can see, when you choose an external wave model, here it pops out other more options for users to select. And also when you start, so after you select include radiational stress, more option can be set up by the users. And then here it allows people to create the wave.imp files. And here, this one allows users to import the SWAN output. And inside the Create SWAN input panel, here you can select all those forcings or the grid that's going to be included for SWAN calculations. And SWAN settings, after you click that, it will pop up this menu, and it will let you allow you to set up some of those computational parameters for SWAN. And then the boundary conditions set up for SWAN can be set up at here. And then at the bottom, this run option is basically let the user to select like where do you want to store all your input files and the executable of SWAN that users is going to use. So after the users run the SWAN model, user can import all those SWAN model output inside the EFDC for further hydrodynamic calculations. And you don't necessarily need to have the same SWAN result, from the same grid, but you can. But it is more recommended. But if you don't have the same grid, then you need to use this for location option. What it does is that users need to provide an additional kind of like those mapping files to let the EFDC to know that where those SWAN model output maps to the corresponding EFDC plus grid. But as long as people are using the create the generate input function from EFDC plus, then in general users don't need to worry about that, and you can just select the from same grid. Yeah, and I think that's all included in this wind wave modeling, and yeah, let's get on to the hands-on exercise.